All right, in this video, we will be going over section 6.1. This section is about volumes by slicing. Okay, we are going to learn various techniques to find volumes of certain objects. All right, I want to start with this example. This is kind of a motivational example. Let's go over this example. Suppose you want to approximate the volume of a sphere of radius 2. Okay, here is what I'm going to do. In order to approximate the volume of a sphere of radius 2, I'm going to consider on the XY plane, I'm going to consider this half circle. Okay, this is the half circle with radius 2. We know that the equation of that half circle would be y is equal to 4 square root of 4 minus x squared. We all know that. Okay, that is coming from the fact that the circle of radius 2, which is centered at origin, would be x squared plus y squared is equal to 4, right? So now if you isolate your y, this is what you get. So that means the equation of this half circle is going to be y is equal to square root of 4 minus x squared. Okay. Now what I'm going to do is, now notice that the radius is 2. Okay. So your radius is 2. Now what I'm going to do is, I'm going to consider this planar region. This is a region on the XY plane. Now I rotate this region around the x-axis. This is my x-axis. I rotate this planar region about the x-axis. If I rotate that region about the x-axis, I'm going to get a sphere, right? Now I'm going to find a way to approximate the volume of that sphere. If you rotate this region again, you get this sphere. Okay, you get a sphere. So now we need to find a way to approximate the volume of that sphere. Let me complete my sphere. Let's say this is your sphere. If you rotate this region about the x-axis, then how do we approximate the volume of that sphere? Well, what I'm going to do is, I'm going to approximate the volume of this sphere using 6 disks. Okay, that 6 is not a special number. If you want, you can approximate the volume using 8 disks, 10 disks, whatever the number. Okay, for the time being, let's approximate the volume of this sphere using 6 disks. What I'm going to do is, I'm going to divide this interval into 6 sub-intervals because I want 6 disks. Okay, so I divide this interval into 6 sub-intervals, 6 equal sub-intervals. Then I can find these points. First of all, I know how to find my delta x. Delta x is going to be b minus a over 2. 2 minus 2 over 2, which is going to be it's not over 2, over 6, because I divide my interval into 6 equal sub-intervals. You get 4 over 6, which is 2/3. Okay. All right. Now I know my delta x. Now I can find these points. I can find each of these points by adding delta x to this number. I will get this one. And by adding 2 delta x to this number, I get this point, and so on and so forth. In fact, we have a formula for that. Xk is given by a plus k delta x. I know my delta x. Delta x is 2 over 3. I can plug in that here. I can find x1. This is x1. This is x1. This is x2. x3. x4. Okay, I can find all these. Pardon me. x3 should be this one. x3 is right here. x5. And of course, this is x6. Okay, this is x0, of course. All right, now I can find each of these points. If you find these points, you will get x1 is equal to, okay, using this formula, I can find x1. First of all, x0 is minus 2. That's clear. That's the starting point. And then x1 is equal to minus 4 over 3. You just plug in k is equal to 1 in this formula. Similarly, x2 is equal to minus 2 over 3, x3 is equal to 0, and so on and so forth. I can find the other terms. Now, what I'm going to do is, I'm going to go to a particular interval. In this interval, I'm going to construct a disk. Okay. The way I construct the disk is, I'm going to find the midpoint of this interval, that is this point. I'll call that xk star, x1 star, because that's the first interval. I will call it x1 star. Okay. I'm going to find this midpoint. I can easily find this midpoint because I know these 2 points. I add these 2 points and divide it by 2 to find the midpoint. If you find the midpoint, you will get minus pi over 3. This midpoint will be minus pi over 3. Similarly, I find the midpoints of each interval. Okay, I'll tell you why I find the midpoints of each interval. Okay, the midpoint of this interval is x1 is equal to minus pi over 3. And then the midpoint of this interval will be x2 star. I'll take that to be x2 star, which is minus 1. Similarly, you can find the midpoint of each interval. I have listed down those midpoints. x3 star is minus 1/3, x4 star is 1/3, and so on and so forth. Okay. Now, what I'm going to do is, I'm going to go to my first interval and I'm going to construct a disk. The way I construct my disk is, I'm going to take the radius of the disk to be this height. I can evaluate this height by plugging x1 star in my function. This is my function. If I plug in x1 star in this function, I would rather call this function f of x rather than saying y. I'll call it f of x. To find this height, I'm going to plug in x1 star in this function. That will give me that height. Now, with that height, I'm going to construct a rectangle like this. With that height, I construct a rectangle. Now, what I'm going to do is, I'm going to rotate this rectangle about x-axis. Then I get a disk, right? The idea is, I can find the volume of this disk. I need to find the volume of this disk. Okay. And I do a similar thing for the next interval also. You go to next interval, you find the height of this function at the midpoint of that interval. And then with that height, I construct a rectangle like this. Now I rotate this rectangle about the x-axis. Then I get a disk in the second interval. So on and so forth. You get bunch of disks. Here is the picture. When you're done this, when you're done with this, here is the picture. You get 6 disks, right? As you can see, the sum of the volumes of those 6 disks would be a good approximation for the volume of the sphere. That's the idea. Okay. So what we need to do is, we need to find the volumes of sum of the volumes of those 6 disks. Okay. So let's find the volume of the first disk. To find the volume of the first disk, it's not hard. So the volume of the first disk, I'll call it V1. Here is my first disk. You rotate this about the x-axis, then you will get a picture like this. Okay, this is a disk. Okay, this is not a two-dimensional thing. This is a disk. You can find, compare that here. This is the first disk. You can find the volume of that disk. How do you find the volume of that disk? I'll call the volume V1 of the first disk. V1 is equal to pi r squared times delta x, right? You find the area of this disk. Area of this disk, that is pi r squared. Of course, I know r. R is this height. Okay, that is pi times r. How do you find r? You plug in x1 star in your function. Okay, that is f of x1 star pi r squared times delta x. Your delta x is 2 over 3. Okay, this will give you the volume of the first disk. Similarly, if I call V2 the volume of the second disk, you will get a disk like this. I'll call this V2. Then V2 will be equal to pi times r squared, that is x2 star, f of x2 star, whole thing square times delta x. Delta x is 2/3. Likewise, you can find V3, V4, V5, and V6. Okay. Now easily you can compute this and get the final answer, right? You can get a numerical answer for this, because all what you need to do is you plug in this x1 star, which is a number that you know, in your function. If you plug that in, this is just a number. This whole thing will be a number. Okay. Likewise, you can find the volumes of the other disks as well. Now what you do is you add up all these disks. Okay. You add the volumes of all these 6 disks. That will give you, if you compute that, I'm not going to show you the computation because they are so straightforward. The volume of these 6 disks would be 33.9758. Okay, all I did was I computed the volumes of these 6 disks. Okay, I have 6 disks. I computed the volumes of all the disks. As you can see, this is clearly an approximation. You can see that from this picture clearly. Okay, but if you want a better approximation, what do you have to do? If you want a better approximation, what you need to do is you need to divide this interval into more sub-intervals. 6 is not enough. If this answer is not accurate enough, you need to divide this sub-interval into this main interval into more sub-intervals. For example, you divide it to 10 sub-intervals, 15. Okay. When you divide that into more and more sub-intervals, then you get a better and better approximation. That's the idea of volume. Okay. Volume by slicing in this section. All right. Let's move on. That's the motivational example. Now let's move on. Now, the next thing I want to discuss is the cross-sectional area. If you know the cross-sectional area of an object, okay, for example, suppose you have a curve. This is your y is equal to f of x, and you rotate this region. You rotate this region about x-axis. If you rotate this region about x-axis, you get a solid, right? You get a nice solid. This will be your solid. Okay. Now, suppose you know the cross-sectional area of this solid. For example, suppose this on the x-axis, this value is x. Then suppose you know the cross-sectional area of this object. At that point, I take a cross-section at x is equal to x, and then I know the area of that cross-section in terms of x, which is given by ax. Okay, so the area of the cross-section at the point x is known. If I take a cross-section at x is equal to x, then that cross-section has an area ax. Then how can we find the volume of this object? Can we find the volume of this object? Again, the idea is same. I'm going to use a similar idea that I used in calculating, in approximating the volume of the sphere in the previous example. Again, here I'm first going to approximate the volume of this object. And then I'll try to see if I can find the exact value of the volume of this object. Okay. The idea is you divide this interval into n equal sub-intervals. Let's say this is the kth sub-interval. Or in other words, this is the point xk minus 1. This is the point xk. Okay. Now, I'm going to pick xk star to be the midpoint. Okay, my xk star is the midpoint of that interval. And I'm going to construct a disk there. I'm going to take the height of the disk to be the height of the function at that point. Okay, with that I'm going to construct a disk. This is, first I construct a rectangle, of course, and then I rotate that rectangle about x-axis. Then we get a disk, right? Clearly we get a disk if you rotate that about the x-axis. We get this particular disk. What I'm going to do is I'm going to find the volume of that disk. Okay, what is the volume of that disk? First of all, At this point, when x is equal to xk star, I can find the cross-sectional area. I have a function for the cross-sectional area. If I plug in this particular point in this function, that should give me the surface area of this disk, right? This is a disk like this. I can find the surface area of that disk by plugging this number, this xk star, in my area function. So I have the surface area of the disk, and I also know the width of the disk. Width of the disk is going to be delta x. Right? Delta x is, by the way, delta x is b minus a divided by n, because I divided my original interval into n subintervals. Okay. So now the volume of that particular disk, I'll call that Vk. The volume of this disk is Vk. Vk is equal to the area times the width. The volume is going to be the area times the width. The area is Axk star, because I need the area of this disk at this point. So I have a formula for the area. I can plug in this point in my area function to find the cross-sectional area. That means the area of this disk times the width of a disk is delta x, which is delta x. Okay. Now what I'm going to do is to approximate the volume of this solid. This is my solid. To approximate the volume of this solid, I'm going to take the summation of volumes of all these disks. Okay, in this interval you have a disk, and then in this interval you have another disk, so on and so forth. In every interval you have a disk, right? Altogether you have n intervals. That means you have n disks. So to approximate the volume of this solid, I'm going to, my volume of this solid, I'll call that V. So I'll write volume of my solid. Volume of the solid is approximately equal to, I take the summation, n goes from, k goes from 1 to n, because I have altogether n disks, a xk star delta x. Delta x is a constant. Okay, I take the summation, sum of the volumes of all those disks. I have altogether n disks. If I take the summation of all those n disks, I should get an approximation for the volume of this solid that you obtain by rotating this region about x-axis. Okay, that's an approximation. How do you get the exact value? As I mentioned in the previous example, if you want a more accurate answer, you need to subdivide this interval into, you need to further subdivide this interval. Okay, you take more subintervals, you get more accurate answer. What I'm going to do is, I'm going to send this n to infinity to get the exact value of the volume. So I'm going to take the limit as n goes to infinity of this expression to get the exact value of the volume. Okay, as n goes to infinity, as you can see, these disks become thinner and thinner. Okay, so that means that will give you the exact value of the object if you take the limit of this expression as n goes to infinity. Okay, motivated by this, we have our next theorem. That's the idea. Okay, the exact volume will be equal to limit as n goes to infinity axk star delta x, and this is by definition of summation. I'm forgetting the summation here. Summation k goes from 1 to n. By definition, this is nothing but the definite integral a to b ax dx. That is by the definition of definite integrals. Okay, so we can find the volume of this solid by this definite integral. Okay, all right. Actually, the next theorem is about what I explained now. Okay, so not a theorem, actually, this is a definition. Let's go over this definition. If S is a solid whose cross sections between x is equal to a and x is equal to b have areas given by a continuous function ax on a comma b, then volume of S is given by this formula. That is, limit as n goes to infinity, summation of ax k star times delta x is equal to the definite integral of ax from a to b. That's exactly what I explained here. Okay. If you know the cross-sectional area at a given point x, then you can use this formula to calculate the volume of that object on the interval a comma b. All right, let's move on. Next, I want to go over this particular definition. Suppose S is a solid of revolution obtained by rotating a region on a comma b around a horizontal axis. If the cross sections of S are disks with radii given by a continuous function r of x on a comma b, then the volume of S is given by this equation. Okay, the volume of S is simply this definite integral, 5 times definite integral from a to b rx squared dx. What does this mean? Okay, let's look at the geometry. Suppose again you are given this function. Okay, this is the function is rx. Suppose this function is r of x, y is equal to r of x. Okay, then as you can see, if you take any point x, this is going to be rx, right? This height is going to be r of x. If this point is x, the height is r of x. Now, suppose you want to find the volume of the region obtained by rotating this region about x-axis. Then you get a solid like this, right? You get a solid like this. You want to find the volume of this solid. Okay. Again, the idea is same. What I'm going to do is I'm going to divide this interval into n subintervals. We can find our delta x this way, b minus a over n. And let's say this is your kth subinterval. On the kth subinterval, I'm going to take the midpoint of that subinterval and find this height. Okay, now I can complete a disk with that height. Then I get a disk like this. Okay, this is a disk, okay, three-dimensional thing. And then I can find the area of this disk, the radius of this disk. Radius of this disk is you just plug in this midpoint in your function rx. Rx is the radius. Okay. Rx is the radius, because if I take any cross section like this on this solid, it's going to be a disk, right? For that disk, you can find the radius of that disk. You can find the radius of this disk by just plugging this number in your radius function. Radius is given as a function of x. Okay, so this height will be, or the radius of that disk would be, if I construct a disk like this, I can find, by the way, the radius of this disk is the height of the function at the midpoint. I plug in this midpoint, which is what I take as xk star in my function to find the radius. Okay, so now if I find the radius, I can find the volume of that disk. Okay, how do you find the volume of this disk? Let me complete the disk. This is your disk. How do you find the volume of this disk? Well, I know the radius and I know the width of the disk. Radius is, of course, rxk star. Radius is going to be, radius of the disk is going to be rxk star. I plug in xk star in my function r to find the radius. Radius means this height. Okay, that will give you the radius, and we know the width of the disk. So we can find the volume of the disk to be pi rk star squared times delta x. First of all, you need to find the area of this disk, that is pi rk star squared, and you multiply that by delta x to find the volume. This is the volume of the kth disk. And of course, you have n disks, so you have to take the summation. K goes from 1 to n, this quantity. And then to find the exact area, you need to take the limit as n goes to infinity. Okay. When you divide this interval into more and more subintervals, you get more and more better approximations. Okay. As n goes to infinity, you get the exact value of the volume. That's the idea. And by the definition of definite integrals, this limit is nothing but pi times definite integral from a to b rx squared dx. Okay, that is by definition of the definite integral. So we have a formula to find the volume of a solid. Okay, volume of a solid with cross sections whose cross sections are disks with radii given by a continuous function r of x. Okay, all right. Let's move on. Okay, let's look at an application of that definition now. Here is the example that I want to go over. Find the exact volume of a sphere of radius 2 by using the definite integral to calculate volume of the solid of revolution obtained by rotating the area under the graph of f of x is equal to square root of 4 minus x squared on the interval -2, 2. Okay. Basically, this is the same example that we took at the beginning. Okay. So this is your circle, half circle. What you do is the equation of this is, of course, f of x is equal to square root of 4 minus x squared. What you do is you rotate this region about x-axis. Then you get a solid. That solid is nothing other than a sphere. Okay. You need to find the volume of that, exact volume of that sphere. Okay. So we can use the previous theorem. Okay. By the previous theorem, if you take any point here, let me first of all complete this sphere. If you rotate that region about x-axis, you will get a sphere like this. Okay. Now, if you go to any point x, and if I take a cross section at that point, that cross section is a circle, right? It's a circle. How do you find the radius of that circle? This radius of this circle is f of x. You just plug in this x value in your function. That will give you the radius of the circle. That means this height. That is f of x. So the radius is known. My r of x in this case is equal to f of x, or square root of 4 minus x squared. So I can apply the previous definition to find the volume of this sphere. Okay. By previous definition, the volume of this sphere is given by pi times definite integral from a to b r of x squared times dx. So you get the volume. Let me write volume. Volume of sphere is equal to pi times definite integral from, remember, -2 to 2. -2 to 2 r of x squared dx. Remember, my r of x is 4 minus square root of 4 minus x squared. The square of that is 4 minus x squared. The square of that is 4 minus x squared dx. All what you need to do is you need to find this definite integral now. Okay. If you plug that in here, you will get the final answer. Okay. If you calculate the definite integral, you should get 32 pi over 3. 32 pi over 3. This is the exact volume of the sphere obtained by rotating this region about x-axis. Okay. This is a straightforward application of definition 6.2. All right, let's move on. By the way, this method is called the disk method. Okay, in this definition, this method is called the disk method because you accumulated disks and then you took the limit as n goes to infinity. So we call it the disk method. The next method I want to talk about is the washer method. Okay, so we define the washer method in this definition 6.3, volume as a definite integral using washers. Okay, let's see what that means. Suppose S is a solid of revolution obtained by rotating a region on the interval a comma b around the horizontal axis. If the cross sections of S are washers with larger radii given by a continuous function uppercase r and smaller radii given by a continuous function lowercase r on a comma b, then the volume of S is given by this formula. Okay, it's the summation. K goes from 1 to n, this quantity, and at the end of the day, you take the limit as n goes to infinity. You can imagine why we are taking the limit. We need the exact answer. That's why we are taking the limit, okay? And that is equal to this particular definite integral, okay? So what does this tell us? By the way, these quantities are defined as follows. These are very standard quantities, okay? You know what is delta x, b minus a o n, xk is defined this way, the same way that we defined in the section of Riemann integrals, and xk star is a number in this interval, and rk star is rxk star, and rk, lowercase rk star is lowercase r of xk star, okay? What this means is that suppose you have a graph like this, and then you have another graph, the second graph, which is like this, and you have a region in between them, right? This is the region in between them. Now suppose you rotate this region about the x-axis, then you will get a solid, right? Solid with an empty interior. This will be an empty region. If you rotate that region, this will be an empty region, right? You just rotate this region about the x-axis, okay? Then you get solid here. So as you can see now, if you take a cross section of this solid, let's say you take a cross section somewhere here, now you don't get disks because this is an empty region. There's no disk there, okay? This is an empty region. In that case, you don't get disk. What do you get? If you have, let's say, vertical cross section like this, you get washers this time, okay? So washers would look like this. And then it's like this. Of course, this is empty, nothing in it, okay? This kind of an object is called a washer, okay? You have material in between those two circles. And suppose this smaller radius is known, which is Rx, lowercase rx. And suppose you also know the bigger radius. Bigger radius means this radius. That is uppercase Rx. Let me actually write it. Let's say the smaller radius, lowercase rx, the upper radius is uppercase Rx. Then what this definition tells you is that you can find the volume of that solid. The solid that you obtain by rotating this region about the x-axis is given by this definite integral. Okay, that's what that tells you. How do you get that volume? What is the thought process behind that? Okay, to show that the volume is given by this definite integral, again, I'm going to consider washers. This time they are not going to be disks, they are going to be washers. Let's say this is your kth subinterval. This is xk minus 1. This is xk. And then I'm going to take xk star to be the midpoint. Xk star is the midpoint of that interval. Okay. And then what I'm going to do is I'm going to construct a washer. Okay, here is how I am going to construct that washer. I'm going to again compute the inner radius at the point xk star. The inner radius at the point xk star would be this radius, right? You all agree with me. And then the upper radius at the point xk star would be this point. Now, with that height, I'm going to complete a disk like this, and then also with the bigger radius, I'm going to construct another disk like this. Okay. Now, as you can see, you have a washer. Your washer is this one. This is your washer. This is your washer. Okay. You have an empty interior. Notice that you have an empty interior. This is an empty region. Okay. So if you rotate this region about the x-axis, you get a washer. Okay. How do you find the volume of that washer? Well, what you need to do is, what I'm going to do is, I'm going to find the volume of this disk and then subtract the volume of this smaller disk from the volume of the bigger disk. The volume of the bigger disk is the volume of this disk. And then you subtract the volume of this smaller disk to get the volume of the washer. Okay. That is going to be, first of all, let's find the volume of the bigger disk. The radius of the bigger disk would be uppercase R of xk star, right? So the volume of the bigger disk would be pi R xk star, R xk star whole thing squared times delta x. That's the volume of the bigger disk. Volume of this disk will be pi R xk star squared times delta x. Okay. And then you subtract the volume of the smaller disk from this bigger disk. So that is going to be pi lowercase r xk star whole thing squared times delta x. That will give you the volume of this washer. Okay, that will give you the volume of this washer. Now what I'm going to do is to approximate the volume of this solid region that you obtain by rotating this region about x-axis. I'm going to accumulate all these washers, the volumes of these washers. I have n of them. So if I take this summation, that will give you the summation of volumes of those n washers. You have n washers here, okay? This is the kth washer. As I showed you, this is the kth washer. Likewise, you take the summation of volumes of all those n washers. That will be this summation. Now, if I take the limit as n goes to infinity, that should be equal to the exact value of the volume of the solid that you obtain by rotating this region about x-axis. Okay. By definition of definite integral, this expression is nothing but this definite integral, pi times definite integral from a to b, uppercase r of x squared minus lowercase r of x squared dx. Okay. So that's the idea. All right, let's move on and see some applications of these definitions. All right, here is the example that I want to look at. Find the volume of the solid of revolution obtained by rotating the region between the graph of f of x is equal to x plus 1 and g of x is equal to x squared minus 4x plus 1 on the interval 1, 4 around x-axis. First of all, let's try to identify the region between these two graphs on the interval 1, 4. On the interval 1, 4, if you plot the graph of this one and this one, you will see that the graph of gx looks like this. And the graph of f of x would look like this. So the region between the two graphs is this region. Now what you do is you rotate that region about the x-axis. Then clearly you get Washer cross sections, right? If you take a cross section somewhere between 1 and 4, clearly you get washer cross sections, right? The cross section looks like a washer because you have this, this region is empty. Okay, so we can use the washer method to find the volume of the object obtained by rotating this region about the x-axis. Okay, so this is a straightforward application of the previous theorem. So we can use this definition. Okay, so first of all, to apply this definition to find the volume of the solid obtained by rotating this region about the x-axis, you need to identify the lower radius and the upper radius. What is your upper radius? What is your lower radius? Well, if you take any arbitrary point x here, the lower radius is going to be this height. Do you know this height? Of course, you know, because you can plug in this point x in the function g of x. If you plug in your x value in this function, you will get the lower radius. This is lower radius. Clearly, your lower radius is r of x is x squared minus 4x plus 5, because this is the function g of x. G of x is this one. And clearly, the upper radius is this side. Right? That's the upper radius. Upper radius is f of x. When at this point x, this height is f of x or x plus 1. So uppercase r of x is x plus 1. So we identified lowercase r of x and uppercase r of x, or the inner radius and the outer radius. All right, now we can go with this formula. We have everything we need. Okay, so the volume of the solid that we are interested is equal to pi definite integral from 1 to 4. Notice that the limit should be from 1 to 4 because we are on the interval 1 to 4. Okay, what is that going to be? 1 to 4, r of x squared, uppercase r of x squared, that is x plus 1 squared, minus lowercase r of x squared, that is x squared minus 4x plus squared, times dx. Okay, so the volume of that solid is given by this definite integral. You know how to integrate this one. This is a very simple integration. Of course, it will take some time. Other than that, it's so straightforward. So this value would be, if you calculate, 73.513 cubic units. Okay, whatever the unit you are using, cubic units. All right, that completes that example. All right, let's go over this example. Find the volume of the cone obtained by rotating the region between f of x is equal to 3 over 2x and g of x is equal to 3 on the interval 0, 2 around y-axis this time. Okay, so how do you find the volume of that region? Well, first of all, let's try to identify volume of the solid that you obtain by rotating that particular region. First of all, let's identify the region that we need to rotate. Okay, so I'm going to graph f of x. This is going to be your f of x, and this is your g of x. This is the region between f of x and g of x on the interval 0, 2. So you need to rotate this region about the y-axis now. Okay, so if you rotate this region about y-axis, you will get a solid like this. This is the solid that you get. Okay, so we need to find the volume of that solid. Notice that now again we can use the disk method. But notice that if you take a particular disk, let's say you take the K disk like this. Okay, now the width of the disk. What is the width of the disk? It is this time delta y. It is not delta x anymore. The width of the disk is delta y this time. Okay, if you take the width of the disk, it is going to be delta y. That means it should be an integration in terms of y, right? Not in terms of x. Okay, so what you need to do is at a general point y, let's say this value is y. We need to find the radius of that cross section. Okay, if you take a cross section here, you you get a disk. Okay, this is the disk you get. This is the radius. Okay, you need to find that radius. Can you find this radius in terms of y? That's the question. How do you find that radius in terms of y? Well, the function is given to us. We are given that f of x is equal to 3 over 2x. So we need to find this value. That means you need to find the inverse of this function, given function, to find this radius in terms of y. Okay, so I'm going to take y is equal to 3 over 2x, and I'm going to find the inverse of that function. Inverse of that function would be x is equal to, if you isolate your x, you get 2y over 3. So your inverse function would be f inverse y is equal to 2y over 3. That's how you find the inverse, right? You take the original function, you isolate your x, you get this one, and this is your inverse function. F inverse y is equal to 2y over 3. So that means I know this radius. This radius is exactly 2y over 3. This radius is nothing but the x value of this function, right? The x value of that function is 2y over 3. Okay, or you can think of that as the inverse function. That is f inverse y. Okay, so this radius is known, that is 2y over 3. Now I can go with the disk method formula, integrating along y-axis. This is the formula for the volume. Volume is equal to pi times 0 to 2. Pardon me, this should be actually 0 to 3, because I have to integrate. Notice that my integration should go from 0 to 3. The upper bound is 3. This is not 2, 3. Let me change it. This should be 3. So what is my r of y? R of y is this radius. This radius is nothing but 2y over 3. Okay, so we have the radius as a function of r, 2y over 3. Now I can go with this volume formula. Okay, so the volume is going to be equal to pi times 0 to 3 0 to 3 ry squared 2y over 3 squared dy. Okay, this is an integration that you know how to perform. Okay, if you find this integration, you will get pi. Okay, that's your answer. All right, this is an example where you need to do the integration along y-axis, not along x-axis. In that case, you need to change the variable to y. Okay, so we need to figure out. You need to figure out what is your ry. Okay, the radius in terms of, you need to figure out the radius in terms of y in that case. All right, let's move on. Right, now let's go over this example. Use definite integrals to express the volume of the following solids of revolution. Here is the first one. The solid obtained from the region bounded by the graphs of f of x is equal to 3 ln x, the line y is equal to 2, and the x-axis and y-axis by rotating around x-axis. All right, let's try to first identify this region, what they're talking about. For that, I'm going to graph the line y is equal to 2. That's clear. That is this line. And then I'm going to graph y is equal to 3 ln x. That's going to be this graph. Of course, it will look like this. But this is the part that I'm interested in. Now I can do one more thing. I can find this value, this x value. How do I find this x value? I can set these two functions equal. I know this function, which is y is equal to 2. This is 3 ln x. If I set those two equal, 2 is equal to 3 ln x, then 2 over 3 is equal to ln x. X is equal to e to the power 2 over 3. So that will give you this value, the intersection point. Now, the region that they are talking about is the region between these two graphs and x and y axis. That is this region. So we need to rotate this region about the x-axis. Then you get a solid like this. You will get a solid like this. This is the solid that you're going to get. Here is your solid. Okay, that's the solid that you're going to get. You need to find the volume of that solid. How do you find the volume of that solid? Well, if you take a cross section in this region, if you take any cross section in that region, they are going to be disks, right? So to find this volume, you can use the disk method. Okay, to find this particular volume, you can use the disk method, the volume from 0 to 1. And then to find the volume from 1 to 2 over 3, e to the power 2 over 3 on this region, you can use the washer method. Because if you take a cross section in that region, they are going to be washers, right? This is an empty region. This is an empty region. So you are going to get washers in this interval. Okay. So the volume will be, volume is equal to pi times, here are the formulas, by the way. I have put down the formulas here. Here is the formula for the disk method. So I'm going to use the disk method formula on the interval 0, 1. If I use the disk method formula, that is going to be 0 to 1 2 squared dx. It is 2 because this radius is constant, which is 2. That's why I have 2 here. This is your r of x, which is 2 constant on the interval 0, 1. And then I have another integral that is again pi times integration 1 to e to the power 2 over 3. This time you have 2 squared, the upper radius. 2 is the upper radius squared minus the lower radius squared. What is the lower radius? Lower radius is 3 ln x. Because I know this height is, if this point is x, this height is 3 ln x. Okay, so I should have 3 ln x squared dx. Okay, that's the integral that we are going to have. That will give you the volume of this solid. All right. Actually, we are not asked to solve the integral. We just have to express the volume in terms of definite integrals. And the volume is given by this particular definite integral. All right, let's move on to the next part, part B. Here is the part B. The solid obtained from the region bounded by the graph of f of x is equal to x squared plus 2 and the line y is equal to 2 on the interval 0, 1 by rotating around the line y is equal to 1. Okay. So first of all, let's try to identify this region. Okay. To identify this region, I'm going to graph these given functions. If I graph that, okay, here is the graph of f of x is equal to x squared plus 2. Everyone knows how to graph that. And this is the line y is equal to 2. the region between the f of x and the line y is equal to 2 on the interval 0, 1 is this region. Okay. Now we are asked to rotate this particular region about the line y is equal to 1. Okay. So here is the line y is equal to 1. This is the line y is equal to 1. Now I'm going to rotate this region about that line. Okay. So this is my region, by the way. This is the region. Okay, I rotate that around this line y is equal to 1. Then you will get a graph. You will get a region like this. Okay, you will get a region like this. Okay, now the question is, how do you find the volume of that solid, which is in black? Okay, you need to imagine that you rotate this area about the line y is equal to 1. Then you get a solid. Okay. Notice that now if you take a cross section like this, they are going to be washers because this region is empty, right? So you are going to get washers like this. So we can use the washers method. But notice that this time we are rotating the solid region about this axis. So you need to find the upper radius and the lower radius with respect to this line. Okay. So the lower radius is clear. That is this height, which is 1. And the upper radius, this is the upper radius. How do you find this radius? That will be your f of x minus 1, right? Because this is already 1. So this radius will be f of x minus 1. Or this height will be f of x minus 1. So let's write down the volume formula now. Your volume would be, volume of the solid would be integration 0 to 1 upper radius squared. Oh, don't forget pi in front. Okay, f of x minus 1 squared minus 1 squared dx. Okay, so that's going to be your volume. Of course, your f of x is nothing but x squared plus 1. Okay, I can rewrite this pi times 0 to 1, integration from 0 to 1, f of x. If you plug in f of x is equal to x squared plus 2, this will become x squared plus 1 squared minus 1 squared is 1 itself dx. This is the volume of this particular solid. Okay. All right, that completes that example. And with that, we complete section 6.1. I'll stop there and I'll see you next time.